Hello everyone, welcome back to another video of Maths 215. I hope you had a good midterm exam and a good weekend. Now it's time to get back to work. Okay, this week and here onwards we're going to start discussing about integrals. Okay, now as you have seen in the coming weeks and the lectures that in the preceding weeks and the lectures that you've seen before with regards to manipulations of complex valued numbers and complex valued functions and complex numbers, the differentiation and all those things, that treating complex numbers is a little bit different and treating complex valued functions is a little bit different, and there comes a little bit of side work when regards to manipulating these things when compared to our very handy dandy real valued functions, which we're very aware of, because that's what we've been doing since we were pretty small kids. Yeah. So let's say I define a complex valued function Wt, okay, meaning a complex number, okay, a complex number which takes a real valued input t. Okay, I'm not saying it's x comma y or r comma theta. I'm just stating, just as a test complex number, that it takes real number inputs t, okay, which is a real number. And of course, since this is a complex number, you can break it down into its real and imaginary number counterparts. So you have u, which is also independently dependent on t, plus I, v, which is the imaginary part, which is again independently dependent on our real parameter t. Okay, now taking the derivative of w with respect to t would hit these real parts and imaginary parts separately, as you may have seen when working with derivatives of complex numbers. So let's see, I'll still show it. So if you hit this complex number Wt with this operator d by dt of Wt, you basically separately differentiate with respect to t of the real part and the imaginary part, as I said so before. So you have u of t plus, u prime of t, as in it's taken, u prime denotes the first derivative with respect to t, plus I v prime of t. Remember, the prime denotes first derivative with respect to whatever you're differentiating with. Here, in this case, it's t. Now, I is being treated as just a simple number. That's why it's just taken out of the derivative. Okay? Since I is not a function, or I is not dependent of t. Okay? In similar fashion, we can set up integrals as well. Yeah? So let's say we try and integrate the function Wt with the element of integration being t, Wt dt, our limits a and b. Similar integration here, this integral operator will hit u of ut and vt separately as well, like how the derivative operator hit u and v separately. Okay, so if it hits separately, it takes the following form. It's Wt, its real part is ut dt, plus, I'm taking the I out of the integral, since I is just, again, it's just a number and it's independent of t, as I said so before. So you can take it out of the integral, like any other normal constant. So I, and our limits again, a, b, and our imaginary part, vt dt. Okay, so there you go. That's how you set up integrals. And this is a very simplistic look. You're going to see how the actual contour integrals look like in the next videos. And it's just the simplistic look and like the heuristic look into integrals regarding complex numbers. Okay, I'll just give a simple example and end this video so that we can move on to the nitty-gritty stuff in the next video. Okay, so say you're given the complex number Wt which is 1 over t plus, sorry, not plus, minus I whole squared. Okay? So we're asked to integrate Wt with limits 1, 2, we have Wt dt. So let's first break this down, okay? Then put it into the integral. I'll first break this down. I should have done it before, sorry. So I'll just break it down right in front of you. So if you just break it down, you get 1 over t squared minus twice I over t minus I, right? Okay, this is what you get. Now, of course, looking at it, you can separate out the real part and the it's not minus 1. Sorry for having so many boo-boos in this video. So we have, no, sorry, not minus I, it's gonna be minus 1 since I squared is 1, minus 1. And then, yeah. So if we take out, we represent all the real parts and imaginary parts separately, as we discussed so before. We have here our limits ranging from 1 to 2, our real part, which includes 1 over t squared, yeah, minus 1, minus, I can bring out twice I, since these are not dependent on t. Here our limits are again ranging from 1 and 2, and we have 1 over 2 dt, and here there's also going to be a dt. Okay, now in computing this integral, we get, I'm just gonna skip over some of the lines, but it's a pretty simple integral. You can do it at home very easily. So computing this entire integral, you get minus 1 over t, yeah, minus 1 over t minus twice I ln modulus of t minus t with the limits set as 2 and 1. Okay? Putting in the upper and lower limits, we have minus 1 over 2 minus twice I natural log of 2 minus 2. And then putting in the lower limit, we have plus 1 plus twice I natural log of 1 plus 1. Okay? Now, taking the natural log of 1 is simply 0, so we can take this to be 0. 1 plus 1, here the 1 plus 1 is 2. 2 minus 2, 0, so we can cancel these three parts. Minus 1, minus 2, plus 1 is just 0. At the end of the day, what we're left with is minus half minus twice natural log of modulus of 2, twice I, sorry, natural log of modulus of 2. You can take the 2 inside, as in taking the 2 inside would simply make it to be a power. So we have minus half minus I ln modulus of 4. And that is your value for your definite integral of a complex valued function which takes inputs t. Complex number which takes inputs t. Thank you, and hope to see you again in the next video.